Hello everyone, welcome to my programming club. Today we will be solving another daily Leetcode problem, and the problem's name is cheapest flights with K stops. So the problem statement goes like this. There are n cities connected by some number of flights. Okay, so you are given an array of flights where each entry in this flights array is of this form. First will be your source city, then will be your destination city, and then it will be the price that it will cost you to uh, travel to from source to destination city. So this indicates that from city source to city destination, we are required to pay this much price. Okay, so you are also given three integers: source, destination, and k. You have to return the cheapest flight from given source to destination with at most k stops. Okay, so the number of stops can be less than k, but it should not be greater than k. Okay, so if there is no such route that with at most k stops you can reach from source to destination, then you should return -1. Okay, so let's see the constraints before discussing our approach. So the constraints are as follows: that n, which is I guess the number of cities, is of order 100, or you can say 10 raised to power 2, and the flights array that will be given to you is having all possible combinations at max. Okay, so n into n minus 1 by 2, it is nc2. Okay, so and the flights length is of order 3. So each entry in flights array is having three things: source, destination, and price. Okay, so then destination and source are ranging from 0 to n, so all cities are marked from integers 0 to n. Okay, and from is not equal to 2, so the source is never equal to the destination for every entry in the flights array that will be given to you. Okay, there will not be any multiple flights between two cities, so it cannot be the case that from A to B there is a flight, and then A to B there is another flight. Okay, so this is never the case, so there are no parallel edges, you can say. Okay, what I mean by this is, so let's say if there is a flight from A to B, then it is never the case that there can be another flight which is A to B, so only single edge will be there. Okay, so and source is never equal to the destination, so the cities between which you are asked to find the minimum price that you have to pay will never be equal. Okay, so source and destination will not be same. Okay, so these are the constraints. Now let's discuss the approach that we'll be using. Okay, although it's a pretty standard problem, just with few minor tweaks, pretty well-known algorithm will be used. Those of you who are new to this particular algorithm that we'll be using, I'll be trying to describe in smallest words, lesser number of words possible. Okay, and I'll also be giving a link of an article describing this particular algorithm and its implementation. So the algorithm that we'll be using is Dijkstra. Spelling is little difficult to write. Dijkstra. Okay, Dijkstra algorithm. For which cases it's used? It's used from single source, so test path. Single source, so test path cases. Okay, so let's say this is the source that is given to you, and we have to know that what will be the distances of all the nodes, shortest distances of all the nodes from this source. Okay, shortest distances of all the nodes from source. What I mean by distance is we are considering price here as a distance. Okay, price is considered as distance. Okay, so it doesn't really matter if you consider price as distance, you can anyhow return the distance, minimum distance. Okay, so single source shortest path, and if we are having minimum distance between source and destination, then we can easily return that. Along with that, what we will be requiring is we will be requiring to tell whether this is possible in at most k stops. Okay, now coming back towards our algorithm, so how we will be implementing it. First of all, two things will be required here. One will be your distance array. Okay, so there, as you can see, there are four numbers here, 0, 1, 2, 3. So let's have a distance array of size 4. So 0, 1, 2 and 3. Initially, let's see the source and destinations what are given to us. Source is given to be 0 and destination 3. So source 0 and destination 3. So we know what is the source and what is the destination, and then there is k. Okay, so this, for now, for simplicity, let's think that there is no k first of all. So let's describe how this particular algorithm will be working. So we know that 0 will be our source. Okay, so initially what you will be doing is this array is distance from source, and we are taking price as our distance. Okay, this is our distance, price as distance. So if you are initially on source, then your price is 0 or distance is 0, and for the very beginning, every distance from source, every node's distance from source will be considered as infinity. Okay, so then what you will be having is you will be having a min heap. Okay, so this min heap will store values in this format. It will be node value, node number, or say, okay, node number and its distance from source, distance of node from source. Okay, node from source. So these two things will be there, and your min heap will be arranged with respect to this particular value, distance from of node from source. So initially you will push only this source value to your min heap, which will be source is here is 0 and its distance was 0. Okay, distance from source. Okay, so this pair will be pushed in your min heap. So your min heap will return you know, at top of min heap you will be having a node which is at smallest distance from the source. Okay, so let's say you pick that node out of the heap. Okay, min heap that you are having, node having smallest distance from source. Okay, so now you are having node having shortest distance from source. Then what you will do, you will relax all the neighbors of this node. Okay, relax all the neighbors of picked node from heap or min heap to be specific. Okay, so what are the neighbors of source right now? One is this 3 and another one is this 2. So since because you know from source there is only there are only two directed edges away from source, that are only 2 and 3. Okay, so initially we know that 2 and 3 are having infinite as their distances from the source, but we are able to find shorter distances here. So since infinity is larger than 600 and it's also definitely larger than 100, so we'll be replacing these values. Okay, if that's not the case, let's say you are at a certain path and let's say these values have been, instead of infinity, 50 and 60. Okay, so if you see that 600 and 100, both of these values are greater than their corresponding nodes distances from source right now. So these things should not be updated. The distance of these nodes from the source should not be updated because we are not finding any shorter path here. Okay, so this is the thing that or trick that Dijkstra algorithm uses. Whenever you find a shorter path to a particular node from source, then you update it. Else, if the path is not shorter than the previously known path, then you leave it as it is. Okay, and whenever you pick a certain node which is having smallest distance from source as of now, from unvisited nodes, okay, so there will be some nodes that you have done visiting. Okay, by visiting I mean that whose neighbors are already explored. Okay, and for the unvisited nodes you will pick the node which is having smallest distance from the source. So this is for the unvisited nodes or unexplored nodes, and you will relax its neighbors. By relaxing I mean that if you are having a shorter distance path from source to the neighbors of the current node being picked, then you will update the distances of neighbors of current node that is picked from min heap, else you will keep it as it is. Okay, so this is what relaxing means. Okay, and let's say if you update some value of a neighbor of the current node, then you will push that node into heap. Okay, sounds good, I guess. And if you are still having any doubts, I'll be providing link of this particular article in which the explanation is very detailed and implementation is also discussed here, so you can definitely check it out. Now comes the part where we have to keep track of only k moves at max. So we should be telling whether it's possible in k moves at most. Okay, for to reach from source to destination. And if that's the case, we should be returning the minimum price, or you can say minimum distance, price taken as a distance. Okay, so let's see how we'll be doing that while adding this little extra thing to our implementation of standard Dijkstra algorithm. Okay, so let's move towards the implementation part. So this is the implementation part, and these two values are of, first of all we will be building a graph. Okay, so graph is having this kind of structure: node, and then neighbors, and with neighbors there will be two things. First will be your neighbor value that is there, or neighbors representation. Okay, so let's say neighbor name, it is in form of integer, and then distance of neighbor from current node. Okay, distance of neighbor from current node. So this graph will be having this kind of structure. Okay, so this and then we will be making our graph. This particular thing is your neighbor. Okay, and this is neighbor's distance from source. Okay, this particular thing. Okay, I guess I copied one extra bracket here, so doesn't really matter, we fixed it. And neighbor distance from source. Okay, and source, if you may ask, well, source is not source is required here, so this is your source, or let's say current source. Okay, so I guess till now you are able to understand. And moving forward, this is the distance from source. By source I mean this source that is given to you in the input of this particular function. Okay, and then once you declare this particular queue, so instead of here using any priority queue or something, we are only using a simple queue. Why are we using only a simple queue? Because anyways this constraint will keep us from visiting more than k nodes, and we can keep a variable minimum distance which will be allowing us to get only the minimum distance from source to destination. Okay, so this variable will be returning at last. Initially we are initializing it with 0 value, maximum value that is theirs, pardon please, and then we are initializing the number of stops that we are taken till now. Okay, till now we are not visited anything other than that we are currently on our source. Okay, So since we are currently on source, then so we will always push its pair to our queue first. Now you may ask, you may be little bit confused that why are we not using priority queue here? Because the reason being that we are to take care of this factor stops. So in order to do so, we are using a simple queue here that will do the work instead of using priority queue min heap. So let's see how we'll be approaching further. Then what we'll be doing is we are here doing a level order kind of traversal. So what I mean by this is, first of all, your first level will be comprising of this particular source. Okay, now your second level will be comprising of these two neighbors of source. Okay, then again their neighbors will be explored, neighbors of these two. Okay, so what is left out? Only this thing is left. So it will be your level 1, or let's say level 0. It will be your level 2, and it will be your level 3. So I missed one here, and then it will be level 2. Okay, so in total there will be 3 levels, and you have to tell whether in at most k levels you are able to visit the destination or not. If that's the case, then you will be updating your minimum length here, else you will not be doing so. Okay, and this is just a standard implementation of Dijkstra. What you are doing here is, if you are having a shorter distance of neighbor of current node, let me write here, if you are having a shorter distance of neighbor from current node, then you will be pushing updated pair for neighbor in queue. Okay, and this thing that you will be taking out from the queue as of now, it do not require to be doesn't require to be the minimum unvisited node that can be there. What I mean by this is, for example, let's say you are at source. Okay, let me again copy this particular image so that I would be able to take it to a new slide. Okay, so let's see what I was talking about. So let's say initially you were at source. Okay, here, then we know that the source is having right now 2 neighbors. One is this 2 and another one is this 3. So since there are only 2 directed edges out of source, so we somehow end up visiting instead of 3 first. Okay, so 3 was initially having 0 infinity as distance from source. So this was your source, and 2 was also having infinity, and this was your queue, and initially your source was there, which is 0. So you picked it out, and instead of adding 2 first, which was having lesser distance from source, you end up adding 3. Okay, so the queue looked like something like this, 3 and 2. So right now when you will be picking the front element of the queue, you will be having a element which is not at the smallest distance among from source among your unvisited nodes. Okay, so that is completely fine with us, since you know we are anyways keeping track whether within k stops we are able to reach our source from source to destination or not. Okay, so if that's the case, then we will update our minimum length and we'll return whether minimum length was updated at all. If it was updated, then it will return the minimum length, else we will be returning -1 to indicate that there is not a possibility that you will be reaching from source to destination within k stops at most. Okay, so this is how we will be solving this particular problem. If you are still having any doubts or any queries in general, then please feel free to ask them in the comment section. Thank you for watching. Have a great day ahead.